In mathematics, in matrix theory, a permutation matrix is a square binary matrix that has exactly one entry of 1 in each row and each column and zeros elsewhere. Each such matrix represents a specific permutation of M elements and, when used to multiply another matrix, can produce that permutation in the rows or columns of the other matrix. Definition: given a permutation I euro of M elements, given in two-line form by its permutation matrix acting on M-dimensional column vectors is the M matrix pi euro whose entries are all 0 except that in row I, the entry I euro I equals 1. We may write where denotes a row vector of length m with 1 inch the jth position and 0 in every other position. Properties: given two permutations I euro and I florin of M elements, the corresponding permutation matrices pi euro and pi florin which act on column vectors can be composed. However, note that if the corresponding permutation matrices are defined to act on row vectors, that is, where is the Kronecker delta, the rule is reversed. As permutation matrices are orthogonal matrices, the inverse matrix exists and can be written as multiplying times a column vector G will permute the rows of the vector. Multiplying a row vector H times will permute the columns of the vector by the inverse of. Again, it can be checked that. Notes: let Sn denote the symmetric group, or group of permutations, on 1, 2, n. Since there are n permutations, there are n permutation matrices. By the formulas above, the n permutation matrices form a group under matrix multiplication with the identity matrix as the identity element. If denotes the identity permutation, then P1 is the identity matrix. One can view the permutation matrix of a permutation I florin as the permutation I florin of the rows of the identity matrix I, or as the permutation I florin of one of the columns of I. A permutation matrix is a doubly stochastic matrix. The Birkhoff-von Neumann theorem says that every doubly stochastic real matrix is a convex combination of permutation matrices of the same order, and the permutation matrices are precisely the extreme points of the set of doubly stochastic matrices. That is, the Birkhoff polytope, the set of doubly stochastic matrices, is the convex hull of the set of permutation matrices. The product Pm, pre-multiplying a matrix M by a permutation matrix P, permutes the rows of M. Row I moves to row I euro I. Likewise, MP permutes the columns of M. The map SNOA-GL, N, Z2, is a faithful representation. Thus, A equals N. The trace of a permutation matrix is the number of fixed points of the permutation. If the permutation has fixed points, so it can be written in cycle form as I euro equals A2. Arc I florin where I florin has no fixed points, then A1, A2. Equal eigenvectors of the permutation matrix. From group theory we know that any permutation may be written as a product of transpositions. Therefore, any permutation matrix P factors as a product of row interchanging elementary matrices, each having determinant of 1. Thus the determinant of a permutation matrix P is just the signature of the corresponding permutation. Examples: equals permutation of rows and columns equals, when a permutation matrix P is multiplied with a matrix M from the left Pm it will permute the rows of M, when P is multiplied with M from the right MP it will permute the columns of M. Permutations of rows and columns are for example reflections and cyclic permutations. Equals permutation of rows equals, the permutation matrix pi euro corresponding to the permutation, is given a vector G. Explanation: a permutation matrix will always be in the form where OE represents the ith basis vector for Rj, and where is the permutation form of the permutation matrix. Now, in performing matrix multiplication, one essentially forms the dot product of each row of the first matrix with each column of the second. In this instance, we will be forming the dot product of each row of this matrix with the vector of elements we want to permute. That is, for example, V equals T, IV equals Guy, so, the product of a permutation matrix with the vector V above, will be a vector in the form, and that this then is a permutation of V since we have said that the permutation form is. So, permutation matrices do indeed permute the order of elements and vectors multiplied with them. See also, alternating sign matrix, generalized permutation matrix. References. Bruldy, Richard A. Combinatorial Matrix Classes. Encyclopedia of Mathematics and its Applications 108. Cambridge, Cambridge University Press. ISBN 0-521-86565-4. ZBL 1106.050001.